Okay, we're going to go back and solve some of the problems that we had skipped. We're going to do, for Gibbs free energy, we're going to look at 18, 19, 22, and 23. And then we're going to summarize some things that are in your notes on page 27 and 28 about the whole concept of Gibbs free energy and thermodynamic favorability. Alright, so there's lots of other ways to calculate Gibbs free energy, and the second way is just like we did with enthalpy and entropy. We just use the table of values. The key thing here is that the delta G for elements, just like for enthalpy, is 0. Okay, so if delta G is positive, the reaction is not thermodynamically favored. If it is negative, it is thermodynamically favored. And if it is 0, it means that you are at thermal equilibrium. Okay, and if you are at equilibrium, your K is also equal to 1. Hopefully you remember that. Alrighty, so let's take a look at some problems. So we are asked to calculate the free energy of this reaction to produce hydrogen peroxide from water and oxygen. And we are given delta G values. So all we have to do here is use the delta G of formation is going to be the delta G of the products minus the delta G of the reactants. And in this case, we're given them in kilocalories per mole. So we're just going to take those values, and remember that the value for an element is 0, which is why oxygen's value is 0. And if I plug the numbers in and I do the calculations, I should get 59.0 kilocalories per mole. Okay, let's take a look at another one. This one, we say we want to find the delta G of the reaction going from diamond to graphite. And I apologize, I have a little bit of an incompatibility issue when I import this. My arrows turned into these fancy A's, and just ignore that or change them to arrows. So here I have a reaction going from diamond in oxygen to make carbon dioxide, and here I have one from graphite in oxygen going to carbon dioxide. So we're going to use basically Hess's law, right? So we are, in order to do that, we have to rearrange the equations to get just what we want, right? So I can reverse the second reaction, and when I do that, I also have to change, I can cancel out everything that's common, and then I can, I have to reverse the charge over the sign of the energy, right? So, and then I can apply delta G is delta G of the products minus delta G of the reactants. I plug everything in, and I should come out with a tiny little negative 3 kilojoules per mole, which means it is spontaneous. Does not mean it's fast. It happens over thousands of years. Alright, here's another one. We want to find the Gibbs equation can also be used to calculate the phase change temperature of a substance. During a phase change, the system is in equilibrium. So the delta G is going to be 0. Okay, so it's asking us to calculate the thermodynamic boiling point, which is the temperature, given the information below. So if it's boiling point, key word, boiling point tells us we are at equilibrium, right? We're in equilibrium, and delta G equals 0. So delta G equals delta H minus T delta S. I set delta G equal to 0. I rearrange the equation by adding T delta S to both sides, and I get this. I solve for T, which is delta H over delta S, and I get 44 kilojoules per mole. I've got to adjust the delta S by using the 10 to the minus 3 to get it to kilojoules, and I get a value of 370 K. That's my boiling temperature. Alright, here's, I think, the last one. Alright, for the reaction of CO2 plus oxygen, carbon monoxide plus oxygen to yield carbon dioxide, I have my delta G, and we want to calculate K, the equilibrium constant. I'm going to use RATLink again, and solve for log of K. And when I do that, Remember, my delta G is in kilojoules. My R is in joules, so I got to change it. Okay, this is moles K. And when I do that, I get 298K. Oh, times 298K, my bad. And then I multiply it out, I get K equals e to the 103, which is about 1.2 times 10 to the 45th. Alright, so it's time to summarize. If delta G is negative, the reaction is thermodynamically favored. If delta G is equal, I am at equilibrium, and my delta G is 0, and my E cell would also be 0, right, if I'm looking at electrochem. If delta G is positive, it is not thermodynamically favored, and my E cell ends up being negative. Okay. Couple of quick points. Common misconceptions. These will come up in probably multiple choice questions. But if one misconception is that if delta G is positive, greater than 0, which means it's not thermodynamically favored, that the process cannot occur. This is not true. You just need an external source of energy. Okay? So now consider the following. Number 1, an electrical current is applied to charge a battery. So this is be the case if you had a dead battery in your car, you needed a charge. You probably describe the equilibrium condition for a battery as dead. It's not dead, it's just at equilibrium. Okay, so delta G is 0. You can recharge it. Okay. Light and photon absorption in the photosystems of a chloroplast causing photoionization during photosynthesis. These are sources of energy used to make that reaction go. You can couple a thermodynamically unfavored reaction with one that is favorable, and that's what's happening between ATP and ADP in biological systems. The other big misconception, this is part of why the College Board wanted us to shift from the term spontaneous to the term thermodynamically favored, is because they believe this misconception is really significant. And that is that if delta H is large and negative, that the process must proceed at a measurable, or you would even assume a fast rate. And this is absolutely not true. So kinetics is really separate from what's happening here with delta G. So if you have a high activation energy, like the reactions are held together really strongly, or you need the perfect collision. So you can have a negative process, a negative delta G, that is very, very slow. Okay? So delta G does not tell you anything about the speed of the reaction. Okay, we're going to stop right there. In this podcast, we're going to take a look at what things affect whether or not a reaction is spontaneous or thermodynamically favored. In the last several sections, we looked at what happens with enthalpy or heat. And what we need to do is not look at just what's happening with enthalpy, but also what's happening with entropy, and combine those as Gibbs free energy to determine whether or not something will react or not. Okay. So we're using the term here spontaneous or thermodynamically favored. Last year we always talked about spontaneity. This year College Board is trying to get us to use the term thermodynamically favored, which really means the same thing. So in order for a reaction to be spontaneous, there's a couple of things that will impact that. One, of course, is the enthalpy, which we've been studying. And as you know, we've been talking about looking at the change in potential energy from reactions to products, and looking at whether or not a reaction is likely to occur. And what we concluded was that if the delta H is negative, which means the reactants have moved to a lower potential energy, which is generally favored, it's why reactions occur, that they are exothermic, and that is a favored reaction. It's more likely to occur. But we also have to look at this concept of entropy. Entropy is S, the symbol for it is S, and it's a measure of disorder. Lots of different terms are used. Sometimes it's dispersal or number of microstates, and it's a way of thinking about the what happens to the system. So the more disordered, if you imagine I had a deck of cards in a card box, those cards are going to be very well ordered, especially if I put them in there by all aces and all twos. But if I drop those on the floor, they are more disordered. That's all we're